Welcome to qnawire.
This is quite an interesting problem. It's very theoretical. So we want to show that this equation for the average velocity, where is the sum of v and v0 over 2, we want to show that this is not valid when we have an acceleration of this form, a plus bt, where a and b are constants. So this acceleration represents an acceleration that's not constant. And to show that this average velocity equation doesn't work here, we're going to need a little bit of calculus. So I know that I can say A is dx, not dx, dv dt, and then we can say from that our dv is a dt, pretty simple. And now we need to integrate. So I'm going to integrate dv and a dt. And the bounds of this integral, I want to go from v0, our initial velocity, to v. And I'm going to go from a time of 0 to time t. And from here, we just get v going from v0 to v. And on the right side, we want the integral from 0 to t. And our acceleration is a plus bt dt. So the left side just comes out to v minus v0. And the right side comes out to at plus 1/2 bt squared. And now I can find an expression for the velocity. It's going to be v0 plus at plus 1/2 bt squared. And now we'll do the same thing that I just did, but with velocity. So I know that velocity is dx dt. And so I can say that dx is v dt. And I'll integrate once again. And the bounds of my integral, I'm going to go from position x0 to x, and again from time 0 to time t. So just like the last integral, we're going to get x minus x0. And our velocity function is what we solved in the last part, v0 plus at plus 1/2 bt squared. So this integral comes out to be, let's see, v0, the first term, we added t. Second term is going to be 1/2 at squared. This term, t squared integral, is going to be 1/3 t cubed, and 1/3 times 1/2 is 1/6 bt cubed. And so I can get an expression for our position is x0 plus v0t. This should be plus 1/2 at squared plus 1/6 bt cubed. And now I'm going to go back to this, what we're trying to show doesn't work. So I have v equals, or average v is v plus v0 over 2. And to make things easier, so we have this function for position and this function for velocity. I'm just going to set v0 and x0 to 0. Because why not? It doesn't make a difference. And so then we're going to get, for our average velocity, we're going to get v over 2, which is going to be at plus 1/2 bt squared over 2. So we get 1/2 AT plus 1/4 BT squared. So that's what we get if we use this equation for average velocity. And now we want to show that that doesn't work. So we know that average velocity is always going to be delta x over delta t. This is always true. And so if we plug in delta x here, actually we don't even need x0 to be 0 because we have delta x. Doesn't matter. But we still know v0 is 0. So this is going to be 1/2 AT squared plus 1/6 BT cubed over our delta t is just t because we're going from 0 to t. And so this is 1/2 AT plus 1/6 BT squared. And now you can see we have this value for the first equation, which is not equal to what we get when we use delta x over delta t. So that says that when our acceleration is of the form a plus bt, which is not constant, then this equation here, v equals half of v plus v0, does not work.